All right, this is a video on solving exponential and logarithmic equations, and we'll start off with an introduction and then do a few solved examples. And really our main goal here is to be able to solve for an exponent without resorting to tech tools like a graphing calculator or something like that, or guessing and checking, okay? That's our main goal. As a quick reminder, I just want to remind you about translating between logarithm and exponential form. So if we have an exponential expression such as b to the y is equal to x, that's equivalent to this logarithmic expression, log base b of x is equal to y. Those are equivalent mathematical statements. They just look different, okay? They're just translated into different form, but they mean exactly the same thing. So we can do that with a more familiar looking exponential equation. 2 to the x is equal to 15. We can simply rewrite it in logarithm form. And as a mental cue, what I always remember when I'm writing something in log form is that logarithms isolate for the exponent. Logarithms are equal to exponents, okay? So x is equal to, and then we write out our log, and then we need to think about where the 2 goes, where the 15 goes. The 2 is the base, and the 15 is what we're taking the logarithm of. Okay, so those are, that's the first step here, is to simply write it into log form if you're looking for an exponent. I hope you can see right now that our calculator might not be able to do a base of 2 logarithm, but our calculator can manage the change of base property. So let's change it into a base of 10. So this turns into log 15 over log 2, and those are common logs, base 10. Just go to our calculator, and I get 3.91 when I round to 2 decimal places. And we can think about as a check, does that make sense? Does 2 to the 3.91 get us 15, which is what we're looking for? And it does make sense. 2 to the 4 is 16, and 2 cubed is 8. So it makes sense that our answer is just a bit under 4. So 3.91 is our solution here. So let's do some examples here, and we can get a little bit more complex. We can you can see that here our exponent for this first example, there's not just an x in it, there's a 3 in it as well, so we'll work with that. First step is really just to isolate for the exponent, and we'll do that by rewriting in logarithm form. Okay, we can apply our change of base property right away. And I'm going to go through all the steps right here. Eventually you'll get proficient enough with your calculator to be able to do this without writing out all the steps, but I think it's useful at first to do that. And then I can divide both sides by 3, and I can get a final answer like that. Let's go to our calculator and do it. And I get a solution of 0.70 when I round to 2 decimal places. So let's go ahead and see what that checks out as. If we multiply that by 3, because our exponent here is being multiplied by 3, we get 2.1. Let's, as a check, see what 15 to the 2.1 is equal to, which probably won't be exactly 285, but I get 294.98. I want to actually try something here and see how that changes if we go out more decimal places. So let's actually redo this problem, but simply write out more decimal places and see if we can get a little bit closer. So I'll write out 4 decimal places, and I get 0.6958. Okay, and as a check for that, let's plug that in, 15 to the 3 times 0.6958, and see what we get here. And I get 285.08. So it's definitely much closer. You can see how a little bit of rounding, when we rounded to 2 decimal places, got us a little bit significantly far off from what we were hoping for. But once we went to 4 decimal places, when we did our check, we got much closer. So let's, as a general protocol, let's go to 4 decimal places for these guys. And I think we'll get obviously more precise answers. Let's do another one. 15 to the 2, or 5 to the 2x is 130. We can rewrite in log form. 2x is log base 5 of 130. We can apply the change of base property and change the base into a base of 10. And then we can divide that answer by 2 as well to isolate for x. Okay. And going to our calculator here, we will get x is equal to 1.5122 to 4 decimal places. Let's think about if that makes sense. Let's double it because our exponent is doubled, so our answer doubled is roughly 3. What's 5 to the 3? 125. Yeah, that's in the ballpark of 130, so our answer does make sense. So those were some examples of solving exponential equations. Here we can actually solve logarithmic equations as well. We're going to go in the opposite direction, go from log form into exponential form. This first one, we have an implied base of 10. It's a common log, so I'll write it in exponential form. 10 squared is 100. Let's simultaneously add 3 to both sides. So we get 103 equals 4x. And we can divide both sides by 4, or excuse me, yes, by 4. And we get x is equal to 25.75. Okay, going into exponential form to solve a log equation. Next, I have 3 separate problems that are very related. Let me number these 1, 2, 3, and 4. And I hope you can see that 2 through 4, I'm essentially giving you the same numbers, but just in different places and showing you some strategies for how we can solve each of these. Okay? So for number 2, we can write in exponential form x to the 5th equal to 2. And then we have to think about how do we solve for x. We can raise both sides to a particular power to get an x to the 1 on the left side, which is equal to x. So I'm going to raise both sides to the 0.2 power. That's an allowable thing to do. And I hope you can see that when we multiply those exponents following our power rules, that turns into an x to the 1 over on the left. And then we need to do 2 raised to the 0.2 on our calculator. And we get 1.1487. So that would be our answer for x right there. It's okay to have a decimal or fractional base of a logarithm. Okay, we solved for x, and x was the base in the original question. Number 3, again, we're going to just go through the same process of turning it into exponential form and solving for x. And this one's the easiest one of the bunch. 2 to the 5th is equal to x. Remember, we're following that, I call it sort of the circle rule, where we kind of make a cycle around the logarithmic expression to turn it into an exponential form. 2 to the 5th is equal to x. X is going to be 32. That was an easy one. And then lastly, we have log base 2 of 5 is equal to x. So maybe you're thinking, just turn it into exponential form, right? 2 to the x is equal to 5, but now we're stuck with, hey, we have to solve for an exponent. Let's get it back into log form to solve for an exponent. So that just gets us stuck, but hopefully you can see that we can just apply the change of base property. Log base 10 of 5 and log base 10 of 2 will be equal to x. So getting a change of base that our calculator can deal with. And I get x is equal to 2.3219 for that one. Okay, so those 3 problems are pretty important because I showed you the unknown variable x in each of the possible different places, and we followed some similar but slightly different strategies to solve for x. Our last problem of this is our most complex one of the video, and we're going to use log properties to solve for x in this case. And you can see that we have a common base of 10, so that's good. We were dealing with the addition of 2 logarithms, which means that's going to be the log of a product, and everything's equal to 1. So think a little bit about what you want to do here. What I want to do is simplify the logarithms, compress the logs together into one logarithmic expression. So I'm going to turn this into x minus 3 times x is equal to 1. Okay, remember the sum of two logs is the log of a product. And now we can rewrite it in exponential form. There's an implied base of 10, so I can say 10 to the 1 is equal to, I'll rearrange this x term, x times x minus 3. Okay, and so I get 10 is equal to x squared minus 3x. Now you might be thinking, well, how the heck do we do this? Looks like we have a quadratic equation we need to solve. So the way we do that, we typically try to get the expression equal to 0, and then we can see if we can factor or use the quadratic formula. So I'll subtract 10 from both sides and rearrange. And it looks like this is factorable right now, which is nice. So I can factor this into x minus 5 and x plus 2. Okay, that would FOIL out, do that binomial multiplication process to get us x cubed minus x squared minus 3x minus 10. And so this implies that x is equal to 5, and this implies that x is equal to negative 2. So you might think, okay, there's our answer right there, right? We need to think about if these numbers work. Okay, so we can imagine plugging them back in. Okay, so as a check, we can think about, okay, does the log of 5 minus 3 plus the log of 5, does that equal 1? Okay, and we could check it on our calculator. Does the log of 2 plus the log of 5 equal 1? Let's actually go to our calculator and try that. And it does check out. Remember, our product property says that the sum of two logs is the log of our product. So 2 times 5 is 10. So does the log of 10 equal to 1? It is, right? That means 10 to the 1 is equal to 10. Let's check the second answer of negative 2. So let's do a second check right here. Is the log of negative 2 minus 3 plus the log of negative 2 equal to 1? Well, I want you to remember that we can't take the logarithm of a negative number, okay? So if you try to do, this turns into the log of negative 5 plus the log of negative 2. Neither of those logs are allowed. Neither of those logs give us a real answer. So that is actually not a solution. Okay, so we can eliminate the solution of negative 2 and realize that our final answer is just going to be x is equal to 5. That's the only solution that works. That was a tricky one. Key message being you need to check your answers to see if they work. Sometimes you go through the full correct process, but you still get an invalid answer. And that's a good place to stop.